Okay, so this video is going to be going through the forces in circular motion problem set that I posted on Teams. So let's go ahead and get started. Let's get right into it. So the first thing that we're going to see here is this problem with this block with a mass of m that's on a rotating turntable. The block is placed a distance of r from the center of the turntable. And the first thing we'd like to do is to find if the block rotates with a constant angular velocity of omega 0, we want to determine what the force of friction is acting on the block. Okay. So what we can do to start with here is to draw what this is going to look like. So here's our turntable, and then here's our block that is some distance of r from the center. This has some mass of m. And this turntable is going to rotate with some angular velocity omega 0. And so with all of these problems, a really good place to start is with a free body diagram. So our free body diagram here is going to look like this. We have our mass of m, we have a normal force, we have force of gravity, and we have some force of friction, right? So this force of friction is going to point towards the center of the circle because this is what's keeping it moving in the circle, okay? So first thing we can do, now that we have this free body diagram, let's draw a coordinate system. So here's our coordinate system. I like to do this in terms of the r direction and the y direction, but you can define this however you'd like. So we're going to sum our forces in general first. So we write sum of forces is equal to mass times acceleration. Let's do our sum of forces in y is equal to may. So this says that this is going to be n minus mg is going to be equal to 0, because this block is not going to accelerate at all in the y direction. It's fixed to stay on this table, and so this says that the normal force n is going to be equal to mg. So we don't necessarily need this right now to solve this problem, but I kind of like to do this ahead of time because I know this is going to be information I'm going to need later. Okay, so the next thing that we can do is we can sum our forces in the x direction. So sum of forces in the, sorry, I'm not using the x direction, I'm using the r direction. And so the sum of forces in the radial direction is going to be equal to just minus F. So the only force that we have here is this force of friction, and this is going to point in the minus r direction, and this is going to be equal to MAR. So here, we know that this is going to be something that's going in a circle, so the acceleration is going to have to do with the acceleration in the radial direction. We know that from our derivation, we can write this in one of two ways. We can say that this is going to be equal to m times minus r omega squared, or this is also equal to m times minus v theta squared over r, okay? Now here, I give you what the angular velocity is, not the tangential velocity or the velocity in the theta direction. And so what that means is that this is the term that I want right here. And so what this says ultimately, and what our answer to part A is that the force of friction is going to be equal to the mass times the radius times the angular velocity, just like this, okay? So that's our answer to part A. Now, when we go on to part B, so this is going to be 1B, when we go on to part B, we're interested in finding what the maximum velocity is going to be in the theta direction. And so when we have this as a maximum, the force of friction in general, we can say the force of friction is going to be less than or equal to the coefficient of friction times the normal force. But at the maximum, it's going to take the largest value that it possibly can, which means that it's going to be F is going to be equal to mu times n. And so we can take the previous equation that we have, slightly modified for our tangential velocity, and so we can say that this is going to be equal to mv theta squared over r, okay? And really this is a capital R because that was the radius that I gave you. So we have our capital R here. So we have our capital R here. And now what we want to do is we want to solve for the velocity in the theta direction. Now we know from what we found before for the normal force is going to be equal to mg, and so this equation that I have written in this line right here can be rewritten so that mu times mg is going to be equal to mv theta squared over r. And we can cancel our mass, because we see that we have a mass common to both sides. So that's kind of interesting. So what we're finding here is it doesn't matter if we have something with a small mass or something with a very large mass. This is going to work out exactly the same way per some approximation you make. So you couldn't do this with like a feather. And the reason for that is because you'd have like air resistance that would kind of impede the motion of the feather. But provided that you do this in a vacuum and you can take, you can say with, or you can say with some certainty that the free body diagram is exactly as I have written here. So exactly how I have the free body diagram written here, this holds up really well. So the last thing we need to do is to find what v theta is going to be. We can just solve this equation algebraically, and so what that says is that v theta is going to be equal to mu times r times g with a square root. And this is our answer to the next part. So we can put a box around that. Okay, so moving on to 1c. 1c was kind of a challenge question. And so for 1c, what I say is that imagine you have some theta as a function of time. Theta of t is equal to theta 0 times t squared over tau squared. So this is going to have some acceleration with theta. So it starts out initially at rest and at the angle theta is equal to 0. And then it's, the angle is going to accelerate. Okay? Or the turntable itself is going to accelerate is what this is saying. So we want to find the time that it takes for this to lose contact with the table. And so what that means is there's a very specific time that we're interested in. So we'll call this time t star. Okay? So there's a special time t star. And what we're going to say ultimately is that mu times mg is going to be equal to m times r times omega of t star, right? So at this very specific time, or when we evaluate this angular velocity at this special time, is when it's going to have this maximum force of friction, okay? So now that we're looking at this equation here, what we need to do is we need to determine what omega of t is. And so in order to do that, what we're going to do is we're going to say that omega of t, by definition, is just going to be equal to d theta dt. And in this case, per the function that I give you, this is d by dt of theta 0, t squared over tau squared. And so we can take a time derivative of this. This is going to give us 2 theta 0 times t divided by tau squared. Okay? So now we have theta of t, or sorry, omega of t. And now we can take this and we can plug it into the function that we have right here. And so that's going to say that mu, let's cancel our m's, because our m's are going to go away. So mu times g is going to be equal to r times omega of t evaluated at t star. And so this is going to be 2 theta 0 t star divided by tau squared. Okay? Now, all we want to do is we want to solve for t star. Okay? So I think that's what I wanted to find here. Determine how long it's going to take. Perfect. So this is going to say that t star, after we do a little bit of algebra, is going to be equal to mu times g times tau squared divided by 2 times r times theta 0. And that is the time that it takes t star in order for this to start to slide out. Okay? So I'm going to reformat some things, and we're going to move on to the next part. Okay, so I realized when I was looking at this answer right here, I missed a square after I was doing the dimensional analysis here. So really, this right here, this is omega squared. So that's omega squared. So this is going to be squared. So this is going to change our answer here. So our answer here when we solve for this, because we're still solving for t star, is going to be, this is going to be mu g over r times a square root times tau squared over 2 theta 0. Okay, so this is the answer to this one. Okay. Okay. So actually, in the meantime, I had already reformatted this, so we're ready to move on to the other question here. So again, this is why it's important to make sure that you're going back and you're looking at your work, because you'll find that even I make mistakes all the time, but I tend to be able to catch the mistakes that I make because I'm checking my dimensional analysis. Usually as I go, but definitely by the time I'm done with a question, I check my dimensional analysis. Okay, so now let's move on to question 2. So we have question 2a here. Now this question is kind of complicated because this is going to be bringing together some of the things that we did with blocks on inclined planes with the circular motion. And in doing this, what we're going to find is we actually have a different coordinate system than we usually use for motion on inclined planes, because when we were choosing those coordinate systems before, we were concerning ourselves with the direction that an object is going to accelerate in or tend to accelerate in. And for this situation, because this is a case of circular motion, there is a component of the acceleration that's going to be pointed towards the center of the circle. Okay, you'll see what I mean in a second. But let's go ahead and first start by drawing a free body diagram for our bus. And so for 2a, here's our bus, okay? And we have some normal force that's going to be pointing in this direction. We have some force of gravity, mg. And the other force that's important here is the force of friction. Because if this is going to be at some maximum speed, what's going to tend to happen here is that the bus is going to slide out of the circle. And so here, that means that the force of friction has to oppose that. Force of friction is going to be parallel to the plane. And so that says that the force of friction here is going to point in this direction. Okay? So this is good. So the next thing that we'd like to do is we'd like to choose a coordinate system. And like I said, this coordinate system is actually going to be a little bit different than the coordinate systems that we've used previously when we've had things on inclined planes, because ultimately we're interested in what's happening to the, we're looking for a component of the acceleration here. And the reason why I'm setting this up like this, you'll see in a moment, is because this radial direction is going to be related to the acceleration in the radial direction that we've defined in our derivation. Okay, so the next thing that we can do, in order to get things in this coordinate system, we can draw in, I'm going to write my f right here because this is the way I tend to like to break these down. We can draw in, so I like to draw these in different colors. So let's draw this along the r direction. So there's these are the components of this normal vector and this force vector, and in the r direction, or here the minus r direction, and here are the components that are in the y direction. Okay, and then here is where the angle theta is going to be. There's theta and there's theta. So make sure you go through and you understand why theta is put there. Ultimately, this is the same theta that I'm defining right here. And there's a little bit of trig that you can go through to show exactly why this angle theta that I have marked is exactly what it is here. So what we see for our force of friction is that this component right here is going to be F sub y is going to be equal to, this is going to be the sine. So this is going to be F times sine of theta, okay? And it is negative, but we're taking that into account here because we have this arrow pointing down. And then this term right here is going to be F r is going to be equal to F times cosine of theta. Again, we're taking the negative sign into account here already. Let's draw our coordinate system labeled here so that we have the same colors. So this is going to be the r direction, and then this is going to be the y direction. Okay, so now let's do the same thing for our normal force. So for our normal force, what we end up seeing is that this component right here, is going to be an n sine of theta, and this component over here is going to be, sorry, this is wrong. So again, don't trust everything that I write here. You want to be sure that you check it yourself. So this is going to be an n cosine of theta, because cosine has to do with what's adjacent to the angle, and this y component right here is adjacent to the angle. And then this is going to be n sine of theta. Okay? So we've got everything broken into components. Now we're ready to, sorry, there's your n sine of theta. It's coming off the top of the screen with the way that I have this cut right now, but you can see that's your n sine of theta. And so now we're ready to write our Newton's second law equations. So we have, in general, the sum of forces is equal to the mass times acceleration. Here we have the sum of forces in the y direction is equal to ma(y), and the sum of forces in the x direction is equal to ma(x). Okay? So now, when we're looking at the sum of forces in the y direction, this doesn't accelerate at all in the y direction. It's fixed, it's stationary. So what that means is that this is 0, and this is also equal to, we can read off the forces in this direction. So we're going to have an n times cosine of theta from our triangle for the normal force minus f sine of theta minus mg is going to be equal to 0. Okay? And for our sum of forces in x, or sorry, this is actually an r for the way that I define this. So this is the sum of forces in the r direction. So f sub r, ma sub r. This is going to be equal to minus f cosine of theta minus n sine of theta. Okay? And this one is not equal to 0 because this is going in a circle. Okay? So let's kind of play around with this a little bit more and add some additional information here. So for the maximum speed that this is going to have, or the minimum speed, the force of friction is going to be maximized. And so that's to say that the force of friction, F, is going to be equal to mu times n. Okay? Additionally, what we can do here is, well, I'll worry about that in a second. But let's plug this guy into these two equations, and let's kind of collect things. The other thing that we can say is that I'm interested in some translational velocity, the velocity that this is moving with, not the angular velocity that's going around the circle. And so that means that this a sub r can be written as a sub r is going to be equal to minus v theta squared over r. Okay, we're told that it's got this radius of capital R from the center. Okay, so now let's plug all of these things in here. And really what we're seeing, if we're counting equations, we have 1 equation, 2 equations, 3 equations, 4 equations. So really this is a system of equations with 4 equations, 4 unknowns. But it's going to reduce drastically when we do the next step. And so the next step is to take this lowercase f is equal to mu times n and plug that into each equation. And then we're also going to plug the a sub r into the other equation. We'll see what we get. So when we do that, we're going to have n cosine of theta minus mu times n times sine of theta minus mg is equal to 0. And then we're going to have minus mv theta squared over r is going to be equal to minus mu times n times cosine of theta minus n times sine of theta. Okay? So now we're down to 2 equations, 2 unknowns. So let's call this equation, we'll put it in a box to denote that they're different than the ones that I have in the circle. So this is equation 1, this is equation 2. So our 2 unknowns are n and v theta. So we're going to have to eliminate n from these equations. And so what I can do first, I'm going to take equation 2, I'm going to multiply by minus 1. That makes everything positive. Kind of nice. Then I'm going to take equation 1, and I'm going to solve for n. So when I do that, equation 1, the first thing I can do is I can move this mg to the other side. So I have an n cosine of theta minus mu sine of theta, and we lost an n there, is going to be equal to mg. We can factor out an n, so n times cosine of theta minus mu sine of theta is equal to mg, or n is going to be equal to mg divided by cosine of theta minus mu sine of theta. Okay? That's important, because now we have what the normal force is in terms of all kind of known quantities. I actually didn't tell you what the mass is, but we're going to see we don't actually need it. So now let's go to equation 2. Equation 2 can be rewritten. So we have mv theta squared divided by r is going to be equal to, and let's factor out our n's again. And I'm actually going to rearrange terms to regroup them. So what this is going to look like is this is going to be n times sine of theta plus mu cosine of theta. Okay? And we're going to take this n that we have here that we solved for, and we're going to plug it in there. So when we do that, this is going to say that this is going to be equal to mg times sine of theta plus mu cosine of theta divided by cosine of theta minus mu sine of theta. Okay? And we're almost there. We're almost there. Now all we need to do is solve for theta. We can cancel an m, because like I said, I didn't give you the mass, and it turns out you actually don't need it. So this works whether it's a bus or whether it's a small car or if it's a bicycle. This all works the same, provided that the free body diagram holds for any approximations we're making. And then we can multiply both sides by r. Multiply both sides by r and take a square root. Okay? So what we see in the end is v theta is going to be equal to r times g times sine of theta plus mu cosine of theta divided by cosine of theta minus mu sine of theta, and the whole thing under a square root. Okay? So this is our answer to part 1, or sorry, part 2a. Let's go ahead and put a box around that. Okay? And you know, I did this really quickly because I kind of, you get experience when you do algebra to realize the faster way to do it. And it's something that's very difficult to teach you, other than to give you problems and have you go through it yourself, and you're going to build up a lot more experience and confidence with doing your algebra as you're doing these kinds of problems. So don't be discouraged if you look at this and you're like, wow, he did it in like very few steps. It's because I've done it a lot, and it's because looking at this, I know what the most expedient way to simplify this is going to be. So keep practicing, and you guys will get there too. And you might even find that there are some shortcuts that you guys find that I don't. That's good. Teach me something. Okay, so part 2b. Part 2b, this is kind of it's a classic kind of thing that physics professors will ask. And most of you guys won't take physics classes beyond 2001 and 2002. But it's a very classic thing for a physics professor to ask, because what they're really getting at is what is the difference between the first problem and the second problem. So the first problem is it's about to slide out. The second problem, it's about to slide in. And really, there's only one thing that changes here. There's only one thing that changes here. So if I draw my free body diagram for when it's about to slide in, what changes is the direction of the force of friction, right? Because the force of friction is going to be trying to oppose this from sliding out, okay? So really, what we want to do here is we just flip the direction of the force of friction, okay? And so originally, let me draw in kind of a different color here, so it's clear that this is what the original force of friction is. So here's our original force of friction. And we're going to erase this when I post this, because it's not going to make a lot of sense if I have two forces of friction here, if you're not seeing me do this. The original force of friction is this green, and then the black is the other one. So when I broke this one into components, you see how here, when I have my coordinate system like this, here's r, and here's y, that originally it was in the minus r direction and the minus y direction. Now, this is going to be in the positive r direction and the positive y direction. So the only thing that changes for this problem is that we have to flip the sign of the force of friction for the first part in the r direction and in the y direction. Okay? So when we look at this, we don't really need to do this calculation again, because what we see is what happens here for the minimum. So here, let's say this is the max. We want to write v theta min, and you can go through the whole process and prove it to yourself if you don't trust this. Now, honestly, you shouldn't. Don't trust me when I say things, because sometimes I make mistakes, but hopefully this is not one of them. All this is going to do is it's going to flip the direction for the x term and the y term for the force of friction. And so that's ultimately going to give me this. So I don't even really need to do the calculation again, because I know that from this argument and comparing the free body diagram that this is going to hold. Now, if this was like an exam question, you should absolutely write out that argument in its entirety, because if you just write the answer, there's no way for us to know if you actually know why this is true, or you might have just kind of like guessed at it and you said, well, maybe I'll just flip some signs and hope for the best. But you need to explain exactly why you're flipping the signs here. So this is ultimately the answer that we get. And like I said, if you really want to, and you should, as practice, go through and do exactly the same analysis that I did in 2A with this force of friction going the other way, the way that I have it drawn in this diagram here. And what you're going to see is that, so here's the r part, this is the theta part, here is the this is this, and I'm going to erase this portion now. So now when it's written like this, you can really see that it truly is just flipped from the way that it was here. So now, again, the component is still the same in terms of the trigonometric ratio. So let's draw this exactly the same way that I had up here. Which color was I using here? This was like this. So here is the angle of theta. Here is also the angle of theta. And I'll write out one more step to really convince you of this. But so this is going to be, here's that. Oop, here is that, and then here is r, and here is y. So the other step that I'm going to write out here is I'm going to write the sum of forces in general. So sum of forces is equal to mass times acceleration. Sum of forces in the r direction is going to be equal to MAR, which is in this case going to be minus n times sine of theta plus f times cosine of theta. And the sum of forces in the y direction is going to be equal to, this is going to be equal to MAY, which we know is 0. So this is 0. And then this is going to be equal to n times cosine of theta minus mg plus f times sine of theta. Okay, and so here what we're seeing again, I mean we can go through the entire calculation. Actually, it doesn't take too long. So this f right here is going to be mu times n. This n is this is also going to be mu times n. So from the sum of forces in y, what we see is n times cosine of theta plus mu times n times sine of theta. Move the force of gravity to the other side, so this is going to be mg. Or factoring out our n, we see that this is going to be n cos theta plus mu sine of theta factored is equal to mg. Or this is n is going to be equal to mg divided by cosine of theta plus mu sine of theta. And then from the top equation here, we have m times minus v theta squared over r is going to be equal to n. So this is going to be minus sine plus cosine. Yes. So this is going to be minus n sine of theta plus mu n cosine of theta. Factor things out. Let's flip the signs because this is going to be then plus, plus, and then this one is going to become a minus. So this is going to be a minus. We can factor out our n, so we're going to have m v theta squared over r is going to be equal to n times sine of theta minus mu cos theta. Take this n that we solved for here and then plug it in there. And when we do that, we're going to see that this is going to be mv theta squared over r is going to be equal to mg times sine of theta minus mu cosine of theta divided by cosine of theta times, or plus mu sine of theta. Cancel our m's. So let's do that in our typical color here, this light blue here. So cancel our m's, move our r to the other side, take a square root. So multiply by r, and then raise the whole thing to 1/2 power. So we see that v theta min is going to be equal to r times g times sine of theta minus mu cos theta divided by cosine of theta plus mu sine of theta. And then we can take a square root. Okay? And what we see is actually that's exactly what I had said before. And it's a good check because you can make that argument. You can say that all that flipped was that force of friction, and that's just going to flip the signs for that in x and y. But it's good to confirm it because you might not be right, or your argument for things that are more complicated than this is inherently going to be more complicated, and you might forget something. So it's always good to make those types of arguments and then check to see if they're true. Okay? So that's going to be it for this video. I hope you guys enjoy. Take it easy.